Hello again, everyone. So it's time to start our next session by Rafał Bielski from CodePlay. So this session is titled Portable SYCL Code Using oneMKL on AMD, Intel, and Nvidia GPUs. Over to you, Rafał.
Hello, everyone. Yes, indeed. I'd like to talk to you about how to run SYCL code with oneMKL on multiple vendors' platforms. And let me start from briefly introducing CodePlay. We're a 22-year-old company working all this time on compilers and libraries for accelerated computing. And 2 years ago, we became a wholly owned subsidiary of Intel, and we joined Intel in the efforts to expand the open ecosystem for heterogeneous computing. We do this through our involvement in oneAPI and SYCL, where we are working both on the standards and the implementations. We also do a few research projects, including those listed here on the right. And let's jump into the plan for today. So the main goal here is to show you how to achieve portability of mathematical computations across GPU vendors using the oneMKL library. And I'll start with a brief refresher of what SYCL is as a programming model, just in case not everyone in the audience is familiar. And then I'll jump on to the main topic, which is the oneMKL, briefly saying what it is and what the interface library specifically can do for you, how it works, how to use it, how to build it, some gotchas and performance. There should be time for questions at the end if anything's unclear. And starting now from a brief refresher of SYCL. It's a single source, high-level standard C++ programming model. So all these keywords are defining what it is. It can target a range of heterogeneous platforms with its implementations. The standard itself, the definition of SYCL API, is provided by the non-profit cross-industry Kronos Group. It's based entirely in standard C++, as you'll see in the next slide, and its well-defined concurrency and memory models are aimed to enable more optimization and performance opportunities for your kernel. It looks like this very briefly. So you can manage devices with queues. You can manage memory with buffers, or there is also another memory model using pointers called the USM memory model. Then you can submit work to a queue which targets a specific device, as shown in the blue box here. And finally, you can execute parallel computations on the device, as shown in the orange box in the middle. So that's your kernel that runs on the device, and this can be executed on any device that the implementations support. It can be a GPU, CPU, FPGA, even more specialized processors. And as you can see, this is really standard C++ code. There are no pragmas, macros, special attributes, language extensions. It's all looking pretty much like C++ 17, which is the base of the latest SYCL standard. And for the implementations, CodePlay specifically, together with Intel, are working on one of the implementations that are out there, which is called the DP-C++ compiler and its associated SYCL runtime library. It extends the LLVM Clang project with SYCL implementation, and it's open source, so you can get it from GitHub in the link shown in the slide. It also comes with a proprietary version that is shipped by Intel as part of their oneAPI toolkit. So that version, as well as the open source version, they support multiple backends, including Nvidia and AMD GPUs. But if you're using the proprietary version, you also need to install plugins from CodePlay's website, linked here, to get the Nvidia AMD support. So that's nice and easy. And what you get with this is very good performance. We always compare many benchmarks across different types of workloads, different types of computations, to make sure that our SYCL implementation provides matching performance to the native programming models for the Nvidia and AMD GPUs, which is the CUDA and HIP. And yeah, you can see our blog post on more details on these performance numbers. And with that, the question is now if you even need to or want to write your own kernels, because if you're using standard computation, standard mathematical operations, you would normally use some libraries that implement them for you in a most efficient way. So this is actually what oneAPI ecosystem also can help you with, specifically through the oneMKL project that I'm talking about today. You might be familiar or used in the past some vendor-specific GPU numerical libraries like the Intel's MKL or Nvidia's cuBLAS, cuSolver, and others. Similar for the AMD ones like RockBLAS, or RockSolver. And imagine if you could be able to use all of them from single source code. That would be really handy, and that's actually what the oneMKL interface library offers you. So you could really write single source code and then run it on many architectures, many machines. You would probably still recompile if you're running on a completely different operating system, but the source code can be still the same, and you can easily port your applications, for example, between different HPC systems in Europe and US, for example, like those listed here, as well as you can run on your own machines, your own desktops, laptops, and so on. So yeah, that's really nice. And let's jump into the details. Just briefly, before I start talking about oneMKLs, let's disentangle what oneAPI means, because it's actually two things. So oneAPI, as the specification and the open standard, is this project governed by the Unified Acceleration Foundation. And there is also the oneAPI toolkit, which is Intel's product that comes with tools and libraries that follow the open standards, but also other tools that come on top of that to help you work efficiently. So yeah, the UXL oneAPI defines the standards, the APIs, and Intel's oneAPI toolkit comes with implementations of these standards, as well as other tools, development tools. Now, oneMKL itself is actually 3 different projects using the same name, slightly confusingly. Hopefully, the naming may be clarified a bit in the future, but right now, something to be aware of is that oneMKL is the open standard API specification, which is the part of the oneAPI standard governed by the UXL. There is the Intel MKL, or usually Intel refers to this as oneMKL as well in their documentation. It's an implementation of the standard of the SYCL API, and it provides the optimized routines for Intel hardware specifically, just for Intel hardware, CPUs and GPUs. That also comes with other things that are not in the standard. So for example, it also offers a C API and a Fortran API for the same routines. And finally, the main focus of today's presentation is the open source interface library on the left, which is sort of a wrapper implementation that lets you use many different backends. So it implements the open standard API and lets you dispatch your work to different backends, as we'll see in a few seconds. There are some links listed in slide 14 for reference. You can look up the specifications, the implementations, and all the open source code. So the one in the blue is the topic of today's presentation. The oneMKL interface library comes with open source implementation, as well as quite good documentation that's hosted in GitHub. And let's see what it can do for you. So as I briefly mentioned already, basically what it does, it dispatches the routines defined in oneAPI specification to different backends. We have the BLAS, LAPAC, DFT, and RNG domains implemented from the standard. We're working on sparse BLAS. I think it's already working for some backends. I'm not sure if all of them. And we haven't yet covered the summary statistics and the vector math, but there is of course plan to cover all of them. So yeah, it implements all these domains, and on the further level, for each domain, it can dispatch the calls you make to a specific backend, which can be vendor-specific library, like the Intel MKL or cuBLAS or RockBLAS for the BLAS domain. There are also open source SYCL implementations of backends. There's Port BLAS and Port I50. These are also supported. But yeah, the Intel, Nvidia, and AMD backends are supported for all these domains that are implemented. So yeah, just to avoid confusion from now on, when I say oneMKL, I will mean the oneMKL interface library, not the standard and not the Intel MKL. All right, so let's see what it looks like to use it. It comes with two types of dispatching. You can do runtime or static dispatch, which means that you can let the library resolve at runtime whether it needs to call AMD or Nvidia or Intel backend, or you could use this in a static way to decide it at compile time. So basically, as in every SYCL application, you have your SYCL queue that defines a specific device. It's tied to a specific device. So when you pass this to a function call from the MKL, it will figure out which backend is the best one for that specific device. And this also means the runtime dispatch means that you can basically compile a single binary that will be able to dispatch to different backends without recompiling. So that's really handy. If you don't want this flexibility, and you want to avoid some tiny overheads of deciding which backend is the right one, then you could also do the static dispatch where you decide at compile time. So in your code, you can specifically create a backend selector. For example, as here, we have an Intel GPU queue, and we tie the backend selector to that, and we can pass that on then to the function call. Behind the scenes, basically what happens for the runtime dispatch is that it has large lookup tables of all the different domains, all the different functions, and all the backend libraries. It dynamically opens and loads code from the backend library that is relevant to your call and your queue. And that oneMKL backend library then directly calls, it translates the oneMKL call into the native vendor implementation. If you do the static dispatch, then you skip the middle part and you go directly to the oneMKL backend library. So an example of what it looks like when you do the runtime dispatch. There is an example in the repository linked here that you can look up. What I did is I used the latest Intel's oneAPI toolkit to compile this together with the latest version of oneMKL interfaces library, and with this compile command that's in the middle, I was able to compile a single binary that can be used to run matrix multiplication on many different devices. So, for example, here on the left, I'm running the same program on an Intel CPU through the oneCL backend. Then in the middle, I'm running this on the integrated GPU from the same chipset. So this is the Intel integrated GPU running through the level 0 backend. And finally, still on the same machine, but now running on Nvidia GPU, discrete Nvidia GPU through the CUDA backend of DPC++. So yeah, that's really handy if you want portability, if you want to test your code on different devices, or you want to port or implement on one device and then run on another. That's all possible with with this, even without recompiling. Then let's move into some details of using the specific domains. Starting with BLAST, which is the simplest. The basic idea is the same for all. You have your SYCL queue that defines your device that you're running on. You allocate some memory. You move some data to that device, so it has access to your, for example, your matrices that you want to multiply, and then you make the call to the oneAPI MKL, the oneMKL matrix multiplication, as in here, passing the queue and your memory object into the arguments. So when you pass the queue, at this point, the oneMKL interface library decides on which backend to dispatch to. And important thing is that all these calls return a SYCL event object. So this is something you can do to synchronize your execution, because all these calls are asynchronous. So you can either wait on this event, or you can pass this event to other calls as a dependency. So then the other call will only execute once this one finishes. All right, let's have a look at another domain now, the random number generation. It has one extra step, because we need to set up some structures on the device before we can generate random numbers. So what we do is we create this engine object passing the queue. At this point already, the backend is picked by the library, and it already does some work on the device that you chose, allocating some structures and pre-computing, setting some things. Then you define the distribution you want to generate, and finally, in your actual computation, you use the RNG generate function, passing the distribution and engine to this call, and getting your numbers into the device memory pointer paths here. One thing I didn't mention, all these examples show the USM memory model, so we're passing pointers here. But the library implements also the buffer memory model, so both can be used, whichever you prefer. And again, we get an event out of this call, and we can wait on it or pass it further as a dependent. Now, the next domain is the DFT. So this is a bit more complex, because there's a lot of different options on how you can run DFTs. So what we have is these DFT descriptor objects that basically let you configure your execution. So you create this object, and then you can call set value on specific parameters. You pass the parameter enum and then the value enum. As for example here, we say in place, and leave all the other as default. You can look up in the documentation and the API specification what options there are to configure, and then once this is set, you do a commit call. So this commit call only takes the SYCL queue, and again, similar as in the RNG domain, this allocate some structures on the device already and does some preparation, so you can then compute the DFT quickly when you actually want to compute. This is the next call here, the compute forward call, where you pass just the descriptor then and your memory address. Again, you take an event out, and then you can wait or pass it on. And finally, the last domain I have an example for is the APAC, so the solver domain. This gets another small layer of complexity, because the algorithm, the procedure requires some local memory on the device to process the algorithm. And what you can do is you first ask the library, ask the API, what kind of what's the amount of memory that will be needed for this kind of problem that you have, given your objects and what you want to do. Then you allocate the memory for that on the device, on on the device basically, and well, here it's using the shared memory allocation, but that still gets to the device eventually. And now having this scratchpad, this memory allocation that can be used by the algorithm, you can pass it on to the factorization call together with the queue, and then you get an event out of it, which you pass to the actual solve API call as the dependency. So this way, if you wait on the event from the second call, you will know that both executed, and they executed in order because they have this dependency, this event dependency passed on. So yeah, that's how these APIs work in short. And a brief mention on how to use it, how to compile your code together with the oneMKL interface library. If you have oneMKL installed on your system, either by your sysadmins or by yourself, and it's all available in the environment, you can just call find package oneMKL in CMake. Then you can link your application, your binaries to the MKL namespace oneMKL target. And similarly, if you want to do the static dispatch, you can link the specific domain and backend implementations for the oneMKL libraries. Now, you don't want to always install it. For example, if you're running things in pipelines somewhere remote, maybe in CI or somewhere, sometimes you want to, on the fly, while you're building your project, you want to also pull the dependencies and build them together. So we can do that with the standard fetch content approach in CMake, similar as you would do with any other source repository, another dependency. There's one difference here, that if you do this this way, you don't get the namespace targets, that they're just oneMKL here. All right. And one thing worth mentioning at this slide is also if you're using the Intel MKL on the same system, I believe the target name, the package name for that is MKL, not oneMKL. So worth being careful not to confuse it. All right, and just one slide on building the project. If you want to build and install on your system yourself, it's pretty straightforward CMake build procedure, like with any CMake project. It comes with a bunch of options that you can specify. They're all documented, so please have a look at the documentation. I think it's quite good for the build procedure. What you really need to do is just to pick which backends you want to compile, which depends on what libraries you have available on your machine and what hardware you're intending to run on. So for example, you can enable the MKL GPU backend, which is the Intel MKL, or the cuBLAS or ROCBLAS and so on. One constraint is that, and it's actually I think the constraint of DPC++ at the moment is you can only target a single AMD architecture right now. For Nvidia and Intel, this is not limited. You can have generic binaries for all Intel and AMD GPUs. All right. Let's have a look at some things to watch out for when using the library. There's just a couple of small things to be aware of. For example, that backend libraries don't all support every feature. So even if you're using oneMKL as this wrapper layer, it is worth knowing at least how the backend libraries work, what options they provide, what they can do, because if the vendor specific backend doesn't offer something, then of course it won't be possible with oneMKL either. So for example, the QFFT backend doesn't support scaling. You have to do it a little bit, way around it, work around it. And similarly, they have different guarantees. For example, the ROCFFT backend can modify input, which the QFFT does not. So yeah, then if you're using variadic APIs, well, this is a general general hint and advice for any variadic functions. The compiler won't tell you if you pass a wrong type, because it cannot determine that. So you will get a failure at runtime, but this is something to be aware of, and cross-check your types that you're passing into variadic functions. Something that often trips people on is the environment setup. Of course, you always need to make sure that the dynamic loader can actually find all the backend libraries, so they have to be available in your LD library path or in your LD configuration on your system. So yeah, the environment has to be set up properly, so all the backend libraries are visible. All right, and one last thing: when you're coming from the Intel MKL, there are some tiny differences in the API. For example, some headers are named slightly differently, like DFTI and DFT.HPP, and enums are namespaced in the oneMKL interface library, whereas they're sort of macros in the Intel implementation. All right, now let me just at the end of the story present some performance numbers to prove that it's really worth having this wrapper layer that can do everything for you on multiple architectures without losing any performance. So what I did here is I just took a basic GEM example with the parameters as explained here, as in the standard GEM API, and I compiled it to run either with native implementations, so calling directly the cuBLAS or HIPBLAS or the Intel MKL, or with the oneMKL interface library, and compared the native implementations to the wrapped code. The code is available actually in the Velocity Bench benchmark suite that's open source, linked here in the slide. And what I obtained with this is the following numbers. So I executed the same code both with oneMKL, which is the same for all architectures, and with the native implementations, which is different for each one, on 7 different devices. That's 6 GPUs and 1 Intel CPU. So I executed it on 3 Nvidia GPUs, 2 AMD GPUs, 1 Intel GPU, and 1 Intel CPU. And as you can see, the timing of the computation is basically the same all across all devices when you use oneMKL as compared to the native implementation. So yeah, there's really no need to maintain 3 versions of the code if you want to port between different systems. You can have just one with the oneMKL interface library. That's basically all. So I hope we learned today about the oneMKL interface library, what it is and how it works, what its place is in the ecosystem, how to use it, and that it provides portability and performance for mathematical computations on GPUs from all major vendors.